Hi guys, this video is on the theorem of maximal idle and prime idle. First theorem we have is R by M, the additive coset of R with respect to M is a field if and only if M is the maximal idle of R, where R is a commutative ring with unity. Maximal idle, M is the maximal idle of R if and only if M is not contained in any proper non-trivial idle of R. Before we move on to proof, we discuss few facts that are prerequisite of the proof. That means that are necessary tools for the proof. First fact to consider is Z is a ring and 2 is an element of Z, and we have 2Z is an idle of Z. And just like that, R by M is a ring and A plus M is an element of R by M. And we have R by M, A plus M is an idle of R by M. Is an idle of R by M. Second fact to consider is we have gamma from R to R by M, the canonical homomorphism. Then gamma and gamma inverse both presuppose idle. That means gamma maps an idle from R to R by M, and so does gamma inverse from R by M to R. Third fact to consider, a field does not contain any proper non-trivial idle. Does not contain any proper non-trivial idle. Now we proceed to the proof. First part of the proof is M is the maximal idle of R is given to us. R is a commutative ring with unity. To prove is R by M is a field. Now R by M is already a commutative ring with unity because R is also a commutative ring with unity. So to prove R by M is a field, all we have to do is, the only thing left to do is, we have to find the multiplicative inverses of each non-zero element. Now we consider any non-zero element of R by M. M is the 0 of R by M, so let A plus M not equals to M, not equals to 0 of R by M be any element of R by M. Now we show that A plus M has multiplicative inverse in R by M. So if possible, let R by M has no multiplicative inverse in R by M. Second, we have R by M, A plus M is an idle of R by M, as discussed earlier. Now R by M, A plus M is not only idle but also a proper non-trivial idle of R by M, because 1 plus M of R by M does not belong to R by M, A plus M, because A plus M has no multiplicative inverse in R by M, and when A plus M is multiplied with any element of R by M, it does not produce 1 plus M. Now third, gamma from R to R by M is the canonical homomorphism, and we have gamma inverse R by M, A plus M is also a proper non-trivial idle of R, because as discussed earlier, gamma inverse presupposes idle. And clearly M is contained in gamma inverse R by M, A plus M, but we have M is the maximal idle of R, so M cannot be contained in any proper non-trivial idle of R, so this is a contradiction. So A plus M has an inverse in R by M. A plus M is any non-zero element of R by M, so any non-zero element of R by M has a multiplicative inverse in R by M, and this shows R by M is a field. Second theorem we have is R by N is an integral domain if and only if N is a prime idle in R, where R is a commutative ring with unity, so R by N is also a commutative ring with unity. So to show R by N is an integral domain, the only thing left to show is R by N has no zero divisors. Now we proceed to the proof. R by N is an integral domain if and only if A plus N, B plus N equals to N implies either A plus N equals to N or B plus N equals to N for all A plus N, B plus N in R by N. Because R by N is an integral domain, has no zero divisors, N is the 0 of R by N, and for any two elements in R by N, equals to 0 implies either first element equals to 0 or the second element equals to 0. Second, A plus N, B plus N equals to N implies either A plus N equals to N or B plus N equals to N if and only if AB belongs to N implies A belongs to N or B belongs to N for all AB belongs to R, because A plus N, B plus N equals to N if and only if AB belongs to N, and A plus N equals to N if and only if A belongs to N, and likewise B plus N equals to N if and only if B belongs to N from definition of idle. Third, we have AB belongs to N implies A belongs to N or B belongs to N if and only if N is a prime idle of R, because from definition This is the definition of prime idol. So we have R by n is an integral domain if and only if n is a prime idol of R, and we have proved the theorem. Now an idol of R is a prime idol if and only if AB belongs to n implies A belongs to n or B belongs to n. For all AB belongs to n, this is the definition of prime idol, and this shows we have proved the theorem.